Donc on va parler de...
So today we will be speaking about different architectures and convolutive as well as recurrent networks. And at the end, I will spend a few minutes speaking about optimization problems to prepare for the seminar by Yann Olivier, who will speak afterwards in greater detail about optimization in connection with deep learning. Let us begin with convolutional networks. We spoke a lot about this last week, of course, but there are many variants that we haven't yet covered. In particular, a mix, well, I will come back to this in a later lecture, but in particular, a mix of convolutional networks with systems for recognizing different objects. It dates back to the start of the 90s, actually, that I spoke of the last time, replicating convolutional networks in a large image to detect multiple objects by sliding the window. But a lot of progress has been made in recent years, especially for object recognition, and I'd like to tell you a bit more about that. At our last lecture, we saw that convolutional networks have increased in depth significantly in recent years and months. And now we have what we call residual networks, going up to 150 layers. It sounds a bit extreme. It's like overkill with the number of layers. But by stacking up these layers, it enables the system to emulate a sort of iterative algorithms. The more layers, the more iterative steps you have, instead of just a neural network with just a few layers, a few iteration steps. If you have 150 layers like this, the layers can carry out relatively complex operations. And these connections enable the system not to be blocked if one layer were a bit degenerate in terms of the weight matrices, in which case the gradient would not propagate properly. So these connections enable the system to eliminate layers that don't really do much and to recruit the layers that were initialized on the right side to do something useful. But as you increase the number of layers, you get closer to a sort of iterative system with a large number of iterations. So with these connections, we could imagine that if the response calls for a certain number of layers, let's say a certain number of steps that can vary with the input, the system can make, let's say, 50 steps, and then use these direct connections to directly connect with the output, and the number of steps can vary depending on the output can vary depending on the input. We don't understand how it works well. It's quite recent. One possibility is that the system can therefore learn a sort of simplified algorithm. We'll come back to that later on when speaking about recurrent networks. For object detection, last week we spoke about sliding windows over an image. It works very well indeed. So, here's an example of this type of method. A figure taken from an article in Overfeed in the ImageNet contest in 2013. This system takes a multi-scale image and applies the convolutional network 220 by 220 at the input with a sliding window, replicating it throughout the image. And for each category, you have a sort of intensity map, if you wish. This is the output of the detection for the beer category. It turns on because it sees the beer, but it can't locate it. Here is on at the right of the image. Here it sees the entire beer. It covers the beer sufficiently to see it. And as you have a high-resolution image, the map is more precise for localization. But it's not good enough for precise localization. The performance criteria here measures how the predicted box is covered with what is proposed. The window is fixed in size, and objects, of course, can have different heights and widths. So it can't give you a very precise prediction. But there's another idea that consists in quite simply adding 4 outputs to the network. The 4 outputs predict the position of the box with the object inside the window. It's exactly the same network, but instead of 200 or 1,000 categories or outputs, or an output for each category, we have 4 additional outputs where we encode the center of the window, the object recognized, as well as its height and width. Now, in the network with these windows, when the network sees a window that is centered on the head, it can infer that the beer goes out of the window on this side and can therefore predict the window's position. Here is the result of these predictions. Clearly, the prediction is quite adequate, and by, as more and more outputs detect the beer, the predictions all overlap more or less. A sort of majority vote to find the window that covers the beer properly. I don't have it, but this type of method works pretty well. To detect objects, there is another method that emerged just a few months after this one. It's called RCNN, Region CNN. And this consists in having a network that detects object proposals and another network that looks at that place more precisely. This was proposed by Rush Golshik, who was at the University of Berkeley at the time and is now at Facebook Research in California, well, in Seattle, in actual fact. This type of method is one of the simplest methods for localization. Later on, I'll speak about even more precise localization using Roland Colbert's technique later on. But in the meantime, I'd like to speak about some applications of convolutional networks that I didn't cover the last time. In particular, the use of convolutional networks to recognize many objects without knowing the classes a priori. Detecting a face, for example, is one example, or recognizing specific objects like monuments or special places. There are millions of them, and we may not have an image of each object, but once you have an image, you can try to compare that image with the images you had before within the field of the features recognized. This is Deep Face, built by Yannick Tagman and Neil Young at Facebook. Facebook uses this for face recognition online. It's not activated in Europe, so you can't enjoy it here, but it is activated in several countries. You download a picture on Facebook, the people in the picture are detected and recognized if they're your friends. That way you can tag it automatically and then ask your friend if the friend accepts to be tagged. Here's how it works. You have a face detection system that's quite fast and simple, and then detecting key points in the face so as to align a sort of average 3D model of a face on the image. We do this so that later on we can apply the texture. We can consider this is the texture applied to this 3D model. We can then rotate the 3D model for a front view. This is exactly what is done here. This model is aligned and then it's rotated in a 3D space to obtain a front view of the face, and we can also unfold the sides a bit. So the image is very well centered. No need to deal with problems with scale and position. Is extremely well calibrated. It's also a convolutional network, and high layers don't use any shared weights. You use shared weights in a convolutional network because if a characteristic, a feature appears at one point in the image, it's unlikely that it's useful to detect it elsewhere in the image. This is why we repeat combinations of weights. The kernel is replicated throughout the image. But if the image is well centered, if the face is well centered rather than the image, we know more or less where the eyes are, the mouth, and so on. No need to detect high-level motives on the entire image. When you do that, the higher layers that are no longer convolutions always have local connections, but each position has a different set of weights, and we can therefore learn to detect different patterns. It is likely that the detectors at the top left here will focus on the eye, these on the other eye, this on the mouth. They will specialize. There are two ways of training a network like this. First of all, by having a collection of faces and training a classifier quite simply. One experiment carried out was with 4,000 categories, I believe. Several pictures of about 4,000 people training the system. And then you remove the last layer. You just use the second to last layer as a features vector. And for each person that you need to recognize, you train a specific classifier for that person. That specific classifier, the different ways of making it. One possibility that if you don't have many examples of each person, and you have far less examples of the person in question than of all the other persons collectively, you need a robust method in terms of the balance of the class frequencies, and must be properly regularized because you don't have many examples for that category. So one good way is with linear SVMs, properly regularized. Another method is with the closest neighbor, a Gaussian rule of density, let's say, a generative model on the features extracted from the neural network. But to do this, you need to make sure that the vectors produced by this neural network go through all the spaces of all faces properly. You must parse well. We use metric learning. You will hear about this a lot by those who are working on natural languages, questions and answers. It's used a lot in that field, but more and more it is being used for images. There are several methods. One that I'll be speaking about in particular, called Dr. Lim, which means dimensionality reduction by learning and invariant mapping, or Dr. Lim, a bit like Dr. No, the James Bond movie. The idea is simple. You take the convolutional network, and you take an output that is not, well, it is supposed to represent a category, but it's just the last layer of the features, if you wish. So just before you would put the classifier, you're not entitled to put the classifier, but you take two similar images of the same person. You send it in the network to identical copies of the same network with the same weights. The two networks produce two vectors, and you will say that you would like these two vectors to be as close as possible to each other. Two images of the same person, maybe different hairstyle, different glasses, a different look, but it's the same person. And you want this vector to encode the identity of the person. and not the instantiation parameters of that picture in particular. So you take the two images and try to bring the two vectors as close to each other with a quadratic distance between the vectors, quite simply. But if you do that without thinking of the rest, this is just a cost function that you minimize. It won't work because the two networks will ultimately ignore the input and take two constant vectors that are equal. That means that you need a contrastive term forcing the vector to produce something different when you produce an image, two different images. Here's another example of the opposite. If you take an image that's very different from the reference image, the system won't learn much about the output vector. It will be already very different. So you need faces that can be mixed up with the reference image so that the vector is relatively close and therefore so that it can be repelled. There are many such techniques for producing or detecting or extracting from a database contradictory examples. There's a lot of literature on that. But what we will do here is quite the opposite. We will repel the two vectors from each other. But to do that properly, with Dr. Lim and well, the idea is quite simple. If you have, okay, let's say that this quantity is the distance between the output of the network for the first shape, still parameterized by the parameters. So I put the distance itself and not the square distance. So Euclidean distance, you can have a quadratic cost to make these two things different in cases, well, this is when x1 and x2 are in the same class. x1 and x2, same class. Another cost function where they're not in the same class. Something like this. A cost function such as this. This symbol with the pluses, that's just for the positive part. With the brackets, it's like the ReLU function, which means if the argument is positive, is the identity positive, otherwise it's zero. So this is what will repel the two vectors with a linear cost until the distance is greater than a certain margin m. You can choose it arbitrarily. It's just a change of scale at the output. Let's say it is a constant. There's a point when either it will be possible for the system to push the vectors away from this margin, in which case the cost may be zero, or it's not possible, in which case there'll be a sort of balance between the quadratic and the linear cost, satisfying all the constraints, trying to cover all the spaces at the output so that the points are properly aligned at the output. The connection of these two terms well, this is what allows us so the total cost function will be the sum of two terms. which will be this distance that I wrote here, the same here, plus this one. We have two coefficients in front indicating if x1 and x2 are of the same class or not. So delta 1, 2 means, tells us if x1 and x2 are of the same class. If they are, we activate this term or this other term, and you calculate the gradient of this box. Do it nice and easily. This is the Dr. Lim cost function. This is an important point, though. I must repeat, there's no square here in this function. It is one here, though, one square root for this function. You don't have to put a square. You can just have a linear cos. It's quadratic, but it's important not to put any squares inside. If you put a square root here, this cost, let me take a horrible color just to show that, tell you that it's not a good idea. The cost would become a sort of reverse parabola, and the gradient here at 0 is null, so that's no good. Meaning that if by mistake the network were to project all the images at 0, 0, there would be no gradients for the output. The cost function would be high, but with a high gradient you can't get out. A lot of people make that mistake and it doesn't work. So no square roots here. There are many such cost functions that people have found over the years. I won't cover them all, but it's the basic idea in metric learning. The same thing here, the cooperative use of convolutional networks and graphic models such as CRF, random fields. Typically, this is what is used to solve a problem such as trying to identify the pose of a body, a human body. You can train a convolutional network to detect the position of key points on the body. For example, the face, the shoulders, the wrist, and so on. But very often, these tags are a bit ambiguous in the real image. You can have false detections of some of these key points. And if there are several people in the same image, you can get people's wrists mixed up. On some faces, you don't have a wrist that appears when the hand is in the back. So you need to carry out a coherent, a consistent interpretation of the relative position of all of this to properly extract each feature. The question is, how do you carry out a precise localization of these characteristic points? It can be approximate with a convolutional network with a lot of subsampling and pooling. The problem is that the output map is of a lower resolution than the input image, so the recognition of the features would not be very precise, giving you activation blocks, but without telling you exactly what are the features that are of interest. This was proposed by Jonathan Thompson, a student at NYU with Chris Bagler, who's now at Google. The idea consists in taking the features maps taken from the network at a certain level before the pooling layers and running a network quite simply on a window. Once you detect the position of the approximate position of the head, you take an image that focuses on that and takes a part of the image, crops it, and produces a smaller convolutional network without pooling. So it can really extract the exact position of this object. It's a bit more costly because you need several networks to run. It's similar to the RCNN network by Risch-Blochit with pre-position of objects for recognition. So this is more for recognizing a small number of classes, such as key points, on a human body. Here's the final result, but there's an additional step that I haven't covered yet, so that you can find a more or less consistent interpretation of all of these points and match them all, taking into account the geometric constraints of the human body. The way to do that is to connect what we could call a sort of graphical model on top of the neural network. It's a sort of factor graph. Instead of giving you a formula, let me explain it to you intuitively. It's quite simple. Here, you take a map for detecting the face. You have an activation around the face. And then you make it a bit fuzzy. A convolution with a small Gaussian kernel or something of that sort. So you a convolution with that giving you a fuzzy image, a fuzzy map. There are two proposals, one here and one there for the face. There's a face of someone you can see more or less here. And also you have a shoulder detector, the left shoulder in particular, that's activated on this and on that one too for some strange reason. Now, the activation here is quite precise. What you need to do now is to make these two maps cooperate. They say that if there's a shoulder here, the face should be there. And that's the role of this map here. What this map does is this. It says if I see a shoulder at the center of my image, this is a sort of likelihood distribution of the relative position of the face. So all the images I've seen, I've noted that the center of the face is at this relative position with respect to the center of this image here, which contains a left-hand shoulder, giving us a proposal, in fact, of this left shoulder, telling us that the face should be more or less over here. And then you take a sort of likelihood map, not really likelihood, so let's say scores. You take the score map of the face. You multiply it by a term, by the score map of the face predicted by the left shoulder. You multiply these two terms, and that eliminates the bad proposals of a face that are not consistent. So all of these operations are like a typical operation that you would use in a Markov chain or a conditional Markov chain with a CRF, with a conditional random field. Since all of these operations are differentiable, you can say that they're part and parcel of this. You will train them with stochastic gradients just like the rest. So this is Sebastian Song worked on this several years ago in his analysis, saying that if you take a convolutional network with many layers and you repeat it many times, you can see the operations done by the local convolutional network as being similar to the inference algorithms of a Markov chain, the graphical model. So no need to use separate methods, Markov fields or CRF on top of a convolutional network. You can see the last layer of a convolutional network as doing more or less the same thing. Jonathan, when he started, he wanted that direct match between the last layer of the convolutional network and a sort of CRF. He realized that through training, he only needed one layer. He didn't need to repeat the operation. Of consistency here, it works well with just one layer, taking into account all the interactions between all the categories, of course. I won't bother you with the results, but he beat several records with this. And now let's turn to more precise methods for localizing objects. Methods, well, the basic idea, it all started about a year ago. I showed you examples of this before, but it's really very recently implemented, just a few months ago, quite simply. The idea with the deep mask method proposed by Pinheiro and Colabert, and later on by WICCV, is not to produce just coordinates of a box, of an object, as I showed you with the example of a beer earlier. There are certain outputs proposing a category, and then you have 4 outputs that give you the coordinates of the box containing the object. Here it's more precise. You take a map, which is the object mask. The system will be trained to produce the category simultaneously and to produce a mask of the object in question. It works very well, oddly enough. So these are examples of proposals of objects proposed by deep mask. And it's quite impressive. There's a team at Facebook working on a system to take part in the Fair Cocoa contest organized by Microsoft. The findings were presented by ICCV last December. It's a complicated system using a sequence where it takes an image, 200 pixels roughly, sends it to a convolutional network, and then takes the features map at several scales, produces a mask by multi-scale refinement. An architecture that's a bit complicated, especially when you look at what's happening in these modules. But it's quite easy to build these architectures by assembling boxes. The gradient is calculated inside, quite simply. The first proposal for a feature, a sort of mask, low resolution proposed and then refined by boxes that see the features at a finer scale to produce a relatively precise mask afterwards. And it works very well indeed to make proposals of objects and to categorize simultaneously. The thing is, when you apply this system, it calls for a lot of computing power because you need to calculate this with a sliding window. For each window, the system produces a mask. The mask, well, the object recognized may not be centered. It will therefore produce a mask that's a bit off. And then you'll have to see in which window the object is entirely in the image to use that one for recognition. And that can take place at several scales and at several sizes of the input window, leading to something that's quite complex. It's been 27 years in the US they've been trying to find how to say this in English, to say something extremely complex, a real labyrinth, what we call usine à gaz in French. I love that expression, meaning highly convoluted. When you put all these pieces together, it's quite complicated at the end with many boxes, each with a complete convolutional network with hundreds of millions of parameters. This object consists in scene specialized networks for each scale of a view of a given object to carry out more precise localization and identification. When you put all the pieces together, at the end it gives us something truly complicated. It calls for a lot of computing power to train this. It works well though. Here are examples I showed you at the inaugural lecture. You can identify people or objects that can only be identified through the context. It makes mistakes. This is identified as a baseball glove. Of course, if it had the overall context, it could identify that the person is playing tennis, but not much likelihood of finding a baseball glove in that scene. So it's rather easy to integrate that. It's not done. But what's interesting here is that it detects all the cars here, the people, but it also detects this as a car, which is technically correct, but that's not what you would have hoped for. Well, this is astonishing. I'm really surprised at the quality of the mask produced for these objects. Here, there's an error here on this poor sheep that was cut in half. In a way, it can count sandwiches, cakes, zebras, and so on. So, a powerful system. But in the cocoa contest, it came second. The winner used a simpler system in a way, the RCNN architecture by Roskorshik, with object proposals and a recognizer. The only difference with this system, which is far more complicated in a way, is that the winning system is the one that came from Microsoft Research Asia using ResNet, a very deep network with 150 layers and all the connections. This convolutional network works better than the others. The difference in performance is sufficient for the entire system to exceed the performance of this one. It was done primarily by Kai-Min He at Microsoft Research in Beijing. He proposed this ResNet architecture and he applied it to many problems, not only COCO, the common object in context, but also ImageNet, pure object recognition without localization, as well as identifying classes of large numbers that are unknown, similar to the problem of face recognition, as I said before, but focusing on objecting specific objects or monuments, geographical places, for example. So, there's an advantage with a sophisticated architecture, but you need a good basic recognizer. The first thing that Facebook's team did when they came back from the ICCV network is that they replaced this with ResNet, and the performance was improved immediately. There'll be a full seminar on speech recognition next week, so I won't cover that. As I said at the inaugural lesson, since a year or two now, convolutional networks have become more and more mainstream, especially largely used today and in future for driver assistance. This is a specialized board made by NVIDIA, the same company that makes graphic boards, integrated in cars so that cars can perceive and avoid obstacles for self-driving. It's an open platform. This is proposed as a platform for engineers and developers, car makers, to build their own systems that have convolutional network tools with libraries so that they can be implemented rapidly. This system can process inputs from many cameras around the car. This is the chief executive of NVIDIA who presented this quite recently. It works quite well. Another company working on this is Mobileye, an Israeli company founded by Nincha Shoshua, a professor at the University of Jerusalem. He founded this company, Mobile Eye, about 10 years ago. 2 years ago, they adopted convolutional networks, implementing it on a specialized chip that they have for visual processing for cars. They're leading the way ahead of NVIDIA since it's already on some high-end cars, such as Tesla, so that these cars can remain on track and avoid pedestrians or brake if the car ahead is too close, and it works quite well. In fact, they use an encoder that is very similar to what we use for robotics project, a mobile robotics, or sort of semantic segmentation of the image where the part that you can cross is in green, obstacles are in red, and the border is purple, so that for each direction they can know the distance for the closest object and then to plan. But these people had a problem. They realized that the convolutional networks worked very well about 2 years ago. At the time, their chips were not really made for running convolutional networks, so they used a big shoehorn to try to make the convolutional network work in their chip. The next generation of chips will be far more efficient for convolutional networks. But it takes a long time, of course, to design a new chip. Or with all the tests, it takes about 2 years, roughly. The idea of localizing objects can be applied to many areas. A lot of people working on possible use in medical imagery for tumor detection. The big advantage with convolutional networks is that they can look at a volumetric image and not just one section, as you do when you look at the screen. But you can carry out 3D convolution, not just 2Ds. So looking therefore at the full image so that you can correlate the various tranches, sections, and identify problematic areas with greater reliability. We're just at the beginning. This was done at the University of Montreal, at Roger Benjo's laboratory. There's a lot of work on this. Not necessarily at universities or public laboratories, but done by a lot of startups and private companies. IBM, DeepMind, they're also working on that. And a lot of startups that see here an opportunity to use these methods for medical imagery. It's a huge market. And this is one application of convolutional networks that will have a significant impact on public health in the future. I can't remember if I covered this the last time or not. The users of Facebook users download about 1 billion pictures each day, and each picture is recognized by at least 2 convolutional networks, one for the face, one for objects. Once again, they're not activated in Europe. If you live in Europe, there's no face model that has been built for you. But all of this takes place in less than 2 seconds. Less than 2 seconds after a picture is downloaded or uploaded, recognition takes place and tagging. It calls for a lot of infrastructure, a lot of systems, software, to manage such a huge influx of information, and a large number of servers required. The exact number of servers is kept a secret, and I can't tell you. Let's now talk about recurrent networks. I'll tell you more at the next lecture, but I would just like to introduce it. Recurrent networks are networks where you observe an input at a time t. The system takes that input, takes it at the previous state. The system state at a previous time produces a new state, and from that internal state, an output is calculated with another network maybe that can look at the input and the previous states and not just the present state. So it's a loop network with a delay, if you wish. By and by, each time you observe an input vector, you go around the loop here and you produce an output. How do you train a network like this with loops? You unfold them in time. If you unroll it, this network in time, and you have a copy of the network at each instant. This is the network at time t, t-1. To calculate here, you take the input at time -1 and so on. The same network that you apply to the next time. You have an observation sequence or desired sequences, desired outputs for a subset, let's say. All of this means training a loopless network that's feed forward. The only difference is that the weights are shared. All these models are identical with the same parameters, the same modules at different times. The same for these. They replicate the same modules with the same parameters, and we can share the parameters between models. This is what you do for convolutional networks and the Siamese networks. We call them Siamese networks because they're two twins attached by the head. So it's not a problem. Conceptually, that's very complicated if you can calculate gradients in complicated networks with the possibility of sharing weights. You can build these networks easily. There are network architectures that are, architectures for multi-layer recurrent networks where you pile up these functions. A first layer here, taking the states at the previous times. Here again, I should have put the Z prime here. And you repeat this, and the outputs are calculated from the state of the last layer. So you can stack up the layers, but there is a problem with recurrent networks. If you unfold the network with too many layers, you have problems with convergence, gradients. I think Yann Olivier will tell you a bit about this. The fact that you have this problem, it was identified by Benjo and Petro Siemens and Eugen Schulber, more or less about 20 years ago. The problem being that if one of these layers is relatively degenerate, if the function calculated zt, depending on zt minus 1 is not properly trained, always producing the same state, this means that the final state will not depend much on the initial state. Meaning that the Jacobian of this network has singular values that are 0 or very small. When you backpropagate the gradients will become very small. Each time you backprop the gradient, you multiply it by the Jacobian of this box, which may be 0 or close to 0, reducing the gradients. As you multiply that over the layers, it will minimize it, and at the end you won't have any gradients. Another problem that Joshua and Patrice identified is that if you want, the reason why you want to use recurrent networks is to be able to store long-term memory for long-term dependency. Recurrent networks are often used for language modeling. Observation is a window of words in a text, and a prediction and the distribution of the next word that you can find in this sentence. In other words, the next word. Now, for the system to work properly, it must remember the sentence structure, so it needs enough long-term memory to contain the last word in a language like German, where the verb is at the end of the sentence in general. You must remember what the sentence was about to see what verb tense should be used at the end. If language modeling is intended to capture the meaning of a story, for example, that really calls for long-term dependency. For long-term dependency, Joshua and Patrice believe that you need memory. With memory, you have stable states in the system, meaning that a stable state is a state where the final state does not depend on the initial state. You can disturb the initial state without changing the end. A computer memory, let's say a bit in RAM, you can disturb it at the initial state, but it will come back to 0 or 1. But this is opening up Pandora's box because computing power of these recurrent networks is the same as for Turing machines. If you have a high dimension of the internal state, you can calculate just about anything using a recurrent network. Complicated algorithms, NP complex algorithms. So, all the things that these networks can learn. So memory. The paper on the limitations of recurrent networks and the fact of wanting to use them for storing long-term memory. If they store long-term memory, in that case, backpropagation no longer works. But that dates back to some 20 years ago, and that put a stop to researchers' liking of recurrent networks. There was a dark period since the 1990s up to about 5 or 10 years ago where people didn't use recurrent networks because of that. But that argument is not quite true, though. Well, yes, it is false. Not false in terms of its formulation, but in its assumptions. No need for memory for calculation, in fact. You don't need to store a stable memory to remember what took place in the past. The best explanation, that's not very intuitive, but I will come back to that at the next lecture, is this: the existence of quantum calculations, quantum computers that don't exist naturally, not really, but let's say in principle. A quantum computer will only carry out reversible operations. It can't have memory in a quantum computer in a way. There can be no stable state. If you have a stable state, well, if several states can converge to the same state, the operation becomes non-reversible all of a sudden, destroying the entire idea of a quantum computing with reversibility. But we can do any computing with a quantum computer, even those that need memory, so no need for stable memory to carry out universal computing. This theorem that says that you can't use recurrent networks because if they must store memory, we can train them, but in actual fact that's not quite true. You just need to build the network so that the operations carried out to calculate the state from the previous state must be reversible in a way. Yeshua and I worked about 20 years on that. We didn't get it to work, but his and my laboratory have been working on forms of recurrent networks where we force inversibility of this function using several methods. And solving this problem, therefore, of the vanishing gradient, as we call it. Another trick to increase the length of dependency of states in a recurrent network with respect to the past is to stack up the layers and make the higher layers updated slower. So a recurrent network updated at each instant. It's like a convolutional network with pooling, where the next layer is always recurrent but is updated 1 times out of 2. With the same iteration, it can see 2 times further in the past. Less of a chance of losing operations, therefore, because this operation was irreversible. You may view this as a sort of convolutional network where this layer looks at 2 times before that at a temporal convolutional network where each layer is also recurrent. Reversible? If you can calculate this, you can calculate the opposite. This objective function and this objective function. Another simpler trick proposed by Thomas Mikolov, Armand Joulin, Samir Chopra, and Michel Mathieu, Marc Aurier-Ranzato in New York, consisted in taking 2 categories of units in a recurrent network. One recurrent category that is updated at the normal speed, and another set of units that evolve, well, slowly, according to your requirements. Now there's a state of this set of units can change very quickly. And this is imposed by the fact that the matrix updating these units are very close to the unit. So this state changes quite slowly. And therefore, it can be used as a context, as a memory, as relatively long-term to determine the next state of the faster units. Simple idea that works pretty well for language modeling, for example. Why blue? I don't know. Anyway, possible architectures for these recurrent networks with several layers. But what I would like to speak about is LSTM, but I will come back to that later on next week when Gabriel Sinev will speak about speech recognition with neural networks. So this is a type of recurrent network that has become largely used in recent years. It's called long short-term memory, originally proposed by Hochreiter and Schmidt-Huber at the end of the 90s to solve this problem of long-term dependency. It's a bit complex, but the basic idea is easy to understand. Each unit in an LSTM recurrent network where this module is repeated as many times as the number of units. The matrices connect all of this. So we have an input. This input goes through subnetworks, calculating the system's input. Here you would have the equivalent of the X that I had on the previous slide. It goes through several layers and enters the unit that you may see as an internal state. This internal state is used, of course, by the output. Well, by another part of the network to calculate the output. What's special about LSTM is that these units have a loop, a weight very close to the unit. Each unit is connected to itself by a back loop. So it's normally slightly less than 1 in terms of its weight. An additional input is calculated from the other inputs, producing a coefficient that can be 0. If 0, this back loop is cut. If the back loop is on, this input is at 1, this unit would keep its state and would just accumulate the inputs that come in, averaging out over time, and maintains its state, therefore, as you go through the loop. But if this unit decides to update, this loop is cut off and the unit is updated.
Alors en fait, il y a le même principe.
You have the same idea to write. Well, you can see this is a sort of memory unit. There's a multiplication here, taking the input so that you can write the input in this memory, depending on this coefficient. If it's 0, nothing is written here, because the memory is preserved. If this input is 1, all of a sudden this input is written into this memory and added to the previous state. Similarly, the internal state here can be activated, influencing the output through another unit, activating the output. In other words, if you take all of these small circuits, it's very similar to a soft version of a memory circuit, static computer memory, or dynamic memory rather. It may be viewed like that in a way, with an input for updating memory, a selection for writing in memory, and a selection for reading memory. It's a sort of small memory circuit inside a recurrent network, if you wish. It works quite well for many applications. It has become a standard module that people test out systematically for many applications. One spectacular application that appeared about a year and a half ago, proposed by Sutskever et al. At Google, they take an LSTM network, stacking several layers, 4 layers, I believe. It takes a sentence let's say in English, and you can see the output vector at the end of this period as a sort of representation of the meaning of the sentence, and then another LSTM network takes this representation and produces words in another language. And the performance of this system at the time was just below that of a conventional system, but combined with a conventional system, it exceeded the state of the art. Recently, people carried out more refined work on this. Shaw, doing his postdoctorate, and was now a professor at NYU in particular, Chris Manning and his team as well at Stanford. They refined this. Not necessarily LSTM, but they use gated recurrent units with attention mechanisms that we'll be covering later on. And with these systems, they can beat current records in translation. So high hopes that translation systems will exceed the performance of conventional systems soon, and maybe can be deployed on the internet. If you're interested by language modeling, there's an article that was just published on Archive by a Google team, examining many architectures using LSTM and convolutional networks, or a mix of both. Training on large-size data, observing words, trying to predict the next word. The system looks not at words but characters directly and predicting the next word, either using a recurrent or a convolutional network. They carried out massive, large-scale trials with results that are truly excellent. About 20 in terms of perplexity scores out of over 1 billion words. All the tests, well, these were the best findings obtained. A lot of progress has been made. It calls for a lot of computing power, of course, unfortunately. So that's it. I'd like to thank you, and I'll now give the floor to Yann Olivier, who will tell us about optimizing neural networks.